Hello, everyone. Wake up. It's time for the last session of the day. So for this last session, you will have an opportunity to discover methodologies who have interest in other datasets than ESM. So I hope this will be the opportunity to have new ideas to deal with your data. And we start with Florence Tupin from Telecom Paris.
Hello, everyone. So thanks for the invitation. So I will talk about deep learning methods for radar image processing. So here is the outline of my presentation. I will first give you a brief introduction about radar imaging and some radar missions. Then I will present the statistical models that we will use in the following. And then I will present you some deep learning methods, and I will insist on self-supervised methods where you don't need any ground truth to train the network. And if I have time, I will say a few words about a new method that we have developed, which is called the multichannel. And then I will conclude. So a brief introduction about radar imaging. So it's to have some information about the Earth. So typically you have a sensor which is on a plane or on a satellite, and you are emitting some electromagnetic wave in the hyper frequency domain. And then you record the backscattered signal that will give you some information about the different elements that you have on the ground. So in fact, if you just send the wave and you record the backscattered signal, you will have a very coarse resolution, about a few kilometers by a few kilometers for each pixel. So what we do is that we combine multiple backscattered signals for a given target on the ground. And this way of combining this signal is called synthetic aperture imaging. And by doing this, we will have a much better resolution, a few meters per pixel on the ground. So why people are using a radar sensor to acquire images? As you will see in the following, the images are not so nice. There are lots of noise in this image. We are using it then because it's their old-time sensor, because they have their own source of illumination. So meaning that we can acquire images even if we have no sun, for instance, or even during night. And but a very important property of this sensor is that they are all-weather sensor. Even if you have a big coverage of clouds, you will be able to acquire images of the ground. And that may be very interesting if you are, for instance, studying tropical areas or areas where you have a heavy cloud coverage. Another interesting property of this sensor is that we have a backscattered signal, which is a complex signal for each pixel, and the phase information is very useful because it carries information about the elevation of the ground or about the movement of the ground if you have many images. So I will illustrate these points in the other slides, and that will provide you a very complementary information compared to optical sensors. But you have a quite important drawback with this sensor is that you have the speckle phenomenon because you are using coherent imaging. So you have interferences between the different waves. And as you will see, it's quite noisy images. So when dealing with the satellite sensor, we have three important resolutions. So the first one is, of course, the spatial resolution. So we have different modes with the satellites, but okay, I would suppose that I have metric resolution images in the following. Another important aspect is the temporal resolution, is the time you need to wait before acquiring a new image of the same place on the Earth. So what we are having now is satellite constellations, meaning that we have many satellites on the same orbit, so reducing the number of days you have to wait before having a new image. And the last dimension that is important is the spectral resolution, or in my case, for radar images, it's the polarimetric resolution, meaning that I will use some different polarization between the waves in emission and in reception. So we have different kind of images for different applications. So the first kind of image is the simplest one. You just have a single SAR image. In this case, you are mostly interested in, let's say, classification, detection of objects on the ground, but you have more interesting modalities, which are interferometry and polarimetry. So interferometry is the situation where you have two different acquisitions with a slight different angles, and you will recover some information about the elevation. So you see, if I take two images and I compute the phase difference between them, I will have this kind of fringes, and these fringes, they just are providing me like level set of the elevation of the ground. And here is kind of reliability of this phase information. And the last case is the polarimetry. So in this case, you are sending a different polarization in emission and receptions. So for each pixel, you have 3 channels, 3 complex numbers. And by computing the complex correlation with the covariance matrix, you will have information about different backscattering mechanisms inside the pixels of your image. So here is a false color, but that will provide you much more information on the different elements that you have on the ground. So, well, at the moment is called the golden age of SAR. So we already had that in the past, but that's especially true now. We have many sensors that have been launched, and especially SWORD is used, for instance, to compute the hydrology, so the level of the different rivers. So that's very important for the climate models. And we also have biomass, which have been sent just at the end of last year. And again, very important information inside these different climate models. But the other side of radar imaging is, of course, as you may imagine, is that defense areas with very high resolution sensor to monitor different activities. So, in the following, before introducing some deep learning methods or deep learning strategies that we may use to process these images, I will say a few words about the statistical model we have for this image, because they will be useful to define the deep learning methods. So for each pixel, as I have said, we have a complex number that is recorded. So here you have an amplitude image. So I don't know but if you see very well, but you have lots of fluctuations of the modulus of this complex number. And here is an illustration of what you have if you want to compare between an optical image and a SAR image. So you see that for a field which is physically homogeneous, of course, you will have just almost one color if you take the panchromatic image. But if you take the radar image, you have this kind of distribution for the amplitude of the coefficient, the backscattered coefficient. So that's because you have lots of interferences between the different elementary scatterer inside each resolution cells. So that's quite difficult to handle this kind of images. But we have a well-defined model, thanks to Goodman, very old model, that tell us that inside a pixel, because of the interferences between the different waves, the real part will be Gaussian, the imaginary part will be Gaussian, so we can predict that we will have this distribution inside this specific field. So if we know the reflectivity, that means, let's say, the mean backscattering values of the field, I have some distribution for the real part, the imaginary part, as I have said, conditionally, of course, to this reflectivity information. Like I deduce the different PDF that, given an observation, I could use to define this statistical behavior. And what is more important is that if I am in the interferometric case or the polarimetric case or the POLINSAR case, which is a combination of both of them, I still have some distribution that I could use that will link the observation, the diffusion vector, or some small empirical averaging matrix locally, linked to the real information that I'm looking for, which is this covariance matrix, which is the expectation of the emission product between the diffusion vectors. So I'm looking for these sigma values, and I have some observation, which are the K or C values in the following. So let's move to some deep learning methods to try to improve the images I've shown you. So I've mostly shown the amplitude image, but you also have the same noise for interferometric or polarimetric images. And I will discuss, so it's a very old problems. We have plenty of family which have been proposed to try to solve and to improve the estimation of these physical parameters that we are looking for each pixel in the image. But today I will mostly discuss, of course, the recent families of, more recent families of deep learning strategies. So I will not really go inside the architecture of the different networks that we could use, but I will mostly discuss the different strategies we could try to define to solve the problem. So the first strategy, which is level 0 that you could apply, would be to take some on-the-shelf denoiser, usually that is well adapted for Gaussian noise. And you could try to define some framework, usually some variational framework, to be able to plug this denoiser inside your strategy. So, well, it's usually very slow methods because you have to call the denoiser inside some plug-and-play framework, so it's not very efficient. So the most common strategy, of course, is this one, which would be the one where you could have some ground truth image, some direct model that could give you some associated noisy image, and then using this pair of noisy and ground truth image, you could take the noisy image as input, put it in a despeckling network, try to do some estimation, and then have some loss that would compare the ground truth and your estimation, and then you could update the weights of the network to try to learn the best way to do the denoising of this image. So that's the usual way, supervised learning framework. And many of the methods we've seen before, they were in a supervised learning framework. But of course, here we have two main problems. First, we don't have any ground truth because you can't have any radar image where you don't have the speckle because you are in a coherent imaging system. Each time you take an image, whatever the resolution you have, you will have this coherent phenomenon that will lead to this speckle phenomenon. So that's the first point. The second point is that you don't have any very, very good direct model where you could say, okay, I've shown you some distribution, but what I've not said is that, of course, I have the point spread function of my system, and that will modify, in fact, the statistics that I will have. So normally for each sensor, you should have a very good modeling of the PSF and the speckle phenomenon, and that's not so easy to have this direct model. So in fact, this framework is not really applicable in the case of star images. So what I would like to describe now is the self-supervised strategies where you don't need any ground truth image and you will just take noisy images, and using the physics of acquisition of the radar images, you can derive some interesting frameworks where you could train the network and have nice results. So before explaining two strategies, I will take a brief look at this work, which is called Noise to Noise. And it was one of the first work explaining how you could train a network when you don't have any ground truth image. And so what it's proven in this work is that, let's suppose you have a pair of noisy image and the ground truth image, and you train a network to find the parameter, which are the theta parameter here, by minimizing the loss, for instance, just the quadratic loss between the ground truth and the prediction of the network. In fact, you will have exactly the same estimation of the parameter if you have only noisy values. Okay, so let's suppose instead of having the noisy image and the ground truth image, this time you have two noisy images, this one and this one. It can be shown that under certain conditions that are here, you will have exactly the same parameters just by training the network, comparing the output of the network on the other noisy image that you have at your disposal. And the conditions are the following. Of course, your two noisy images, they should see the same underlying ground truth. Okay. The second condition, very important, is that the noise in each image should be independent. And the last comment is that, okay, of course, maybe it's not exactly the same loss that you should use in this situation and in this one, because here you are comparing two images without noise, and here you are comparing a noisy image with something without noise. So what you usually should use is a negative log likelihood, which means you are just trying to evaluate the likelihood of the noisy image given your estimation without noise that you are trying to find. Okay, so what is nice is that this framework is really very well adapted for SAR imaging, because for satellite imaging, because when you are dealing with satellite images, after some time, because the Earth is rotating, you will see again, as I said at the beginning, you will see again the same ground image, okay? So we have the first condition. So I could take a first image taken at some time t1 and then wait until I have a new acquisition, time t2. I give to the network the image at time t1. I ask to have some prediction, and then I compute the likelihood of the image at time t2 to be able to update the weight of the network. So, okay, that's fine. I have to check the different condition. Do I have the same underlying scene? So that's okay if I'm just waiting for the new acquisition. But the second point is the speckle independent between the two acquisitions. So you can check these points. And what will happen if you the problem is that the underlying scene may have changed between the two acquisitions. So you have to find a way to compensate for the different changes, temporal changes that you may have between these two acquisitions. But the network, let's suppose we don't have any change, by having two noisy realizations, because it can't predict the noise because they are not correlated between the two acquisitions, it will just predict the common part between the two images, just the expectation, in fact, of the image, and that's exactly what you are looking for. So I will not really detail the way you could compensate for the different changes, but okay, you can try find a way to do the compensation between the two acquisitions. And then you just train the network by using different pairs of temporal images that you have on the same area. So here is an example on the Sentinel-1 images. So here you have the noisy image. Here you have the noise image. So I don't know if you see very well, but you have some water areas, very black here, and some urban areas where you have very bright points because of the double bands that you may have on the urbans. Okay, you can extend this kind of strategies when you have different channels. For instance, if you are in polarimetric situation, okay, it's not as easy as what I've shown you just with a gray level amplitude image. So this time you have to take the matrix logarithm of the covariance matrix that you are looking for, but okay. Apart from a little bit of maths, that's almost exactly the same as what we've seen before. And what is interesting is that here, again, even in polarimetry, we had to do the change compensation. But you see, for instance, for some modes of the sensor, so here is an example of Sentinel-1 acquisition. You see here, Sentinel-1, it has a very specific way of acquiring images, because in the TOPS mode, the sensor is trying to have a very wide area that is image. And in this case, it will have some pointing angles that will be moving during the acquisition. So what will happen, you will see a part of the image with a certain angle, and then you will see it again, but with a different angle this time. So what does it mean? It means that on the overlap areas, I have two speckle realization, but independent of the same underlying scene without any changes between the different acquisition. So I can just apply the framework you've seen before, but in a way that you don't even need to do change compensation. And that's very important because for interferometry, for instance, it's not possible to have temporal pairs of interferometric images because the baseline between the acquisition, it changes all the time. So that is the only way of applying this kind of strategies, and that's why it probably has the award because of that. Okay, but anyway, you have the way of having this equivalence for interferometric images. So, but the most interesting strategy is this one, because in this case, we don't even need to compensate for the changes. And what is the idea in this part is that when you have a SAR image, for each pixel, you have a complex number. And that's great because you can just take a look to the real part and the imaginary part. And in fact, what happens is that they are both encoding, of course, the underlying reflectivity that you have for the image. And you can show, that was my slides at the beginning with the Goodman model, that the speckle in the real and imaginary part, in fact, they are independent. Okay, so what does it mean? It means that I can just split my image. I put the real part as input to the network, and then I train the network to predict something. And then I have a look and evaluate the likelihood, what the neg log likelihood of the imaginary part given this prediction. Okay, and I can update the weights of the network. And what is great now that I don't need change compensation. And for every archives of SAR images that you have, you can just apply this kind of strategy by splitting the real and imaginary part. So that's a very efficient method. You have, of course, a full analytical way of defining the loss because you have in this case, very simple distribution because you just have the Gaussian distribution. So what happens, you take your image, you take the real part, and you train the network by just controlling with the imaginary part, and that will give you some estimation. That's for the training, and then when you are in the inference part, you can have an estimation using the real part. You can use the same network to have an estimation with the imaginary part, and you can just make the average of the two to have the final estimation. So here is an illustration. You have the radar image. Here is the real part. You can do an estimation. Here is the imaginary part. You can do an estimation, and that's the final estimation. What is really nice, well, already, interesting in this approach is that you are training a network with something which is even worse than the original image. Because, in fact, by just taking the square of the real part, you have an image which is even not a single look image. It's an image with half a look. Okay, so that's destroying the information, but having the independence is a way to be able to train efficiently the network. Okay, I will skip the other results, and I will just say really very briefly an extension of this method of splitting the real part and imaginary part in the case where you have a multi-channel image, meaning not just one complex number for a pixel, but a small vector of complex numbers. So we've seen that we could do some extension in the temporal ways. That's different references I've shown before. But what we were interested in was, could we do something about this idea? So it's not possible just to split the vector in the real part and imaginary part, because that would not fulfill the independence condition I have spoken about before. But what you can do, let's suppose you have just two images. Two complex image. For instance, in interferometric framework, you have just two channels. What you can do is to generate projections. So you just take some vectors of projections and you compute the projection of this image, and that will give you a range of new complex images that are fully defined by the projection vectors that you have chosen. But each of these images, they are complex images, and I could just apply the strategy I've shown you before, splitting the real and imaginary part and training a network to be able to denoise these different new complex images. What is interesting is that the covariance matrix, the sigma matrix I'm looking for, it is fully connected to this new estimation of the speckled images of this acquisition. So now I just have to recombine this projection, just using, for instance, the least square estimators. to be able to recombine all this new estimation and have a new denoised covariance matrix. So it's very simple. I just apply the strategy I've shown you before by using some projection vectors that are well chosen. Okay, I skip the maths behind that, just showing you that I have a link between what I'm looking for, this covariance matrix, and the new estimation without noise that I have obtained by applying my despeckling I have spoken about before. Okay, so that will give you, so here it's just an averaging, local averaging that is widely used in a radar community. And here is the estimation that you would obtain by applying this projection and estimation I've shown you before. So here is a different projections that will be the noise and then recombine to be able to obtain the covariance matrix. Okay, maybe I will just conclude about this, about the talk. So my main message would be, okay, we have this deep learning methods, data science stuff and so forth, but what is always very useful is to try to, so here is an interferometric example. So here you have the original image, and maybe one day we have the denoised image. What is interesting is to be able to include the physics of the acquisition. For instance, the fact that you have complex numbers or the fact that you have a new acquisition that will come back again. So here is the denoise with the projections that I have explained before. And I'm just concluding about that. Maybe you could think that just reducing the speckle or improving the estimation is not something so useful. But what happens is that when you are doing this noise reduction, you are building some representation space that is then very useful if you want to do downstream tasks. So for instance, if you want to classify images, if you want to compute the movement of some parts of the image, compute the elevation, all these tasks which are higher level, they will be much more easier if you are combining them with a despeckling task, because the despeckling task will, in fact, in a way, have some structuration of the latent space that will help you then to compute elevation or to compute, for instance, building detection or classification. And of course, you can adapt this kind of framework to tomography or to different, more complex tasks that you may have in radar imaging. Okay, thanks a lot. You can find the code here if you want to do radar imaging. Sorry.
And the slides are on the Google, so
yeah.
You can take it. Any questions for Florence?
So you didn't describe it. So you said that you're training a network, but what kind of network is it? It's
Yes, here it's very simple network. Is a UNet-like, convolutional network.
And so
let's say.
How do you? I'm interested to know how do you deal when because what I do not completely understand in what you're saying is that you have the plans going over, so he will see the image at different angle, and so I understand when you're using the imaginary and I understand, but when you don't do that, I don't understand how you're correcting for the fact that the scene is moving, in fact.
I understand your question, but here, when I was talking about the multi-channel cases, it was either interferometry, where the difference of incidence angle is so small that the registration is such that you have exactly the same pixel. If you don't have that, you can't do interferometry. And the other example was with polarimetry, where in fact with polarimetry, you are sending waves with the different polarization and you have exactly for one pixel. But what you are saying is mostly something related to radar grammetry or things where you are using the displacement of the object because of the elevation. You can also train networks to do that, but that's what not the subject of this presentation.
Any other questions?
So, is there a limitation in signal-to-noise ratio?
A limitation in the?
In the signal-to-noise ratio of the initial image?
Well, in fact, what I have not mentioned is that there is some limitation to preserve the fact that the real part and the imaginary part is independent. And that means that the complex spectrum of the image should be symmetric. So there are some conditions that I have not really said, but not, well, I mean, anyway, if the signal to noise ratio is so bad in some areas, usually this framework, they will just, have, smooth everything.
And they will smooth it there will be an offset, or will they smooth it to zero?
No, it's supposed to be unbiased because of the loss we use.
To ask the same question in another way, do you have some result where you were disappointed by the result? Because the one you showed are amazing, but were you sometimes disappointed?
Yes, in fact, the Mucha Pro approach that we have published very recently, what we have seen is that we have some influence of the phase information. When we do the projection, we can have a mixture of the amplitude information and phase information and can create some artifacts in some places. So we are trying to control the network.